Hi, my name is Grace Drew, and this is my Physics 2211 Lab 5 Falling Object with Initial Velocity. So, as an introduction to this lab, the purpose is to compare predicted versus experimental velocity of a falling object with initial velocity by using computational experimental models. So basically, this video is just somebody throwing a ball up and down, and then they recorded data which I collected and used for this lab. The method we used was to model the observed motion first. So that video was used on tracker and the results of the position and velocity of the ball were recorded. And then a computational model was created using GlowScript. And those results were also compared to the results from the observed in order to see how the two compare. So we found that the predicted and observed motions were very similar, but the difference was due to GlowScript not accounting for air resistance, and we'll go into that a little bit later. So some key concepts we need to know for this lab, first of all, are Newton's second law. So F net equals delta P over delta T, and it can be written as both a velocity and position update formula. VF equals VI plus F net over M times delta T, and then final position equals initial position plus average velocity times delta T. Next, we're going to need to know the force of gravity. We use this in our GlowScript code in order to model the object falling back down to the ground. And so that's just the vector 0, negative mg, 0, with g being the gravitational constant of 9.8. Other useful equations we'll need to know is the translational kinetic energy equation and then the gravitational potential energy equation. So as I said, for this experiment, I used somebody else's video and data that they recorded of them throwing a ball up and letting it fall back down. But I used my own computational model coding to model the predicted. So as you can see here, some initial conditions we had to put in were the ball's position, which initially was 0. That's why in the graphs you'll see later it goes into the negative. The velocity, which started as a predicted 0.30. This is just an estimate of what it was in the video in order to get a good comparison. Obviously, we started at time equals 0, and the time step we did was 0.033. Our gravitational constant, as stated earlier, is 9.8. And then j hat, which is the difference in the y direction, is also the vector 0, 0, 0. And the b equals 0 just states that the only force we're taking into account is a gravitational force. And this obviously is what causes the difference. So the calculation loop that matters the most is calculating W, which is negative ball M, which is the position of the ball, times gravity times j hat, which shows you the position of the ball due to the force of gravity. So obviously F net equals W. And then the ball's velocity, which is the velocity update formula stated earlier, and then the ball position update formula, which is also the formula stated earlier. So here you can see both the velocity and position versus time graphs, comparative, and there's tracker and GlowScript. The tracker is in blue, the GlowScript is in red. And you can see that they are fairly similar, not too much different, but for the tracker one versus the GlowScript, the tracker always takes a little bit longer to fall back down. So the force of gravity is not as strong, you could say, when interpreting these graphs. This is because in the GlowScript model, we do not account for air resistance. So on the way back down, the only force acting upon it is gravity, which is a negative force, versus there being a small air resistance force upwards. That is modeled in the tracker version, which is why you see that those objects fall slower, but not necessarily slower. It's just a little bit more realistic. And then some possible sources of error for this lab.